Suggest structural optimizations.
Execute refinement.
Optimizations complete. Final specifications locked.
Pro, AI Plus. We need to shift this. AI-powered tier is the future. Let's make it AI-powered tier
Over the
Nigidal.
last decade, our primary technical challenge became the sheer volume of unstructured digital data, audio waveforms and raw pixels that resist simple categorization. Traditional machine learning algorithms were not designed to process this specific type of high-density information. These systems rely on feature engineering, where a human programmer must manually define the exact rules and mathematical parameters the computer uses to identify a pattern. This graph illustrates why the industry shifted. While machine learning hits a performance ceiling regardless of data volume, deep learning is built to ingest raw data directly, allowing its accuracy to scale as more information is provided. This structural shift forced a compromise. We exchanged the step-by-step, human-readable logic of machine learning for raw, opaque processing power. To see why this matters, consider a standard classification task, identifying a piece of rotten fruit. In a traditional machine learning model, an engineer must manually code thresholds for specific colors and write geometric rules to detect surface deformation. The model fails when decay moves in an unpredictable direction. A hard-coded system cannot anticipate the infinite nonlinear variations of organic rot. This limits the utility of any model that relies on manual rule design. Deep learning addresses this by using raw datasets, such as the Fashion MNIST clothing library, as a training baseline. The system bypasses the need for human-defined feature extraction. When the network receives an image of a shirt, it flattens the visual information into a two-dimensional grid of cells. Each cell instantly fills with a specific number. These integers sit on a scale from 0 to 255. A value of 0 indicates complete mathematical darkness in that specific pixel. A value of 255 represents maximum brightness. The system then normalizes the data, dividing every individual cell by 255. This division compresses the varied pixel values into a standard compressed range. All the raw visual data now exists as a value between 0 and 1. This math is then fed into a structure modeled after biological neural pathways. The decimals enter the network through the input layer. From there, they flow into hidden layers for high-speed calculation. The final results appear in the output layer, which uses 10 neurons to represent the 10 possible clothing categories. By converting images into normalized decimals, the architecture analyzes mathematical structure directly from the raw input, removing the need for humans to define visual rules. Within those hidden layers, the core of the process happens inside individual nodes, or neurons. Every neuron operates on this core equation. Its value is the sum of the inputs multiplied by their weights plus a bias. The weight represents the mathematical importance the system assigns to a specific incoming feature. The bias is a baseline adjustment added to the sum to correct the final prediction. This value then passes through an activation function, which determines the neuron's final output. Functions like ReLU zero out negative values to introduce nonlinearity. This is the mathematical mechanism that allows the model to map complex, curved data patterns rather than just straight lines. The system learns through a multi-step training mechanism, beginning with the forward pass. Data travels from input to output to generate an initial prediction. Initially, without any training, this prediction is wrong. The system identifies the degree of failure through a loss calculation. The standard evaluation metric used here is mean squared error. This is the average of the squared differences between what the model predicted and what the answer actually was. The goal of the training is to reach the local minima, the mathematical point of lowest possible error. To reach that point, the system uses backpropagation. Feedback on the error flows in reverse through the network. This backward flow automatically adjusts thousands of internal weights to reduce the error margin. Humans manage this loop through specific hyperparameters. Epochs define how many times the entire dataset passes through the model. Batch size determines how much data the computer processes at once before updating the weights. The learning rate sets the speed at which those weights are updated. Because the system independently updates millions of internal weights over thousands of cycles, a human observer can no longer trace the specific logic behind a final classification. This is the origin of the black box. This autonomous training introduces a technical risk: overfitting. Overfitting occurs when a model memorizes the noise in a dataset instead of learning the generalized patterns. The architectural solution is the dropout layer. This layer randomly deactivates a percentage of neurons during the training phase. This forces the network to develop redundant pathways, ensuring it builds robust, generalized recognition patterns. The shift from manual machine learning to these neural architectures resolve the limits of human-coded rules. These models require massive amounts of data, and their performance continues to scale as that volume increases. But that performance required a structural trade-off. We sacrificed the highly interpretable logic of traditional models for the superior accuracy of deep learning. In complex tasks, processing unstructured data autonomously is the only path to scale. This makes the system's opacity a necessary consequence of its performance.